discussing the particle-like nature of light. You'll hear the phrase particle-like or wave-like properties for light and eventually electrons as we go through here. And just to start, the defining characteristic of a particle is that it has mass. So if you are particle-like, you are going to act as if you have mass, whether you have mass or not. And if you are a wave, the defining characteristic of a wave is that, as we discussed in Roman numeral 1 of this lecture, outline 8, then when you are run through the double slit experiments on a screen opposite the source of the particles or waves, whatever of the waves, you will see an interference or diffraction pattern. So that's where we're going. We're talking about light right now, and we're going to talk about the particle-like nature of light. Now, light and all electromagnetic radiation exists as discrete packets called photons, each with an energy. The equation is E energy equals H, which is Planck's constant, times frequency, and H is 6.626 times 10 to the negative 34th joule seconds. And therefore, from this equation, energy and frequency are directly proportional and related by the constant, Planck's constant, H. Energy and frequency are directly proportional. As an example of a calculation you could be asked to do, say, on the homework or an exam for the, this used to be the 3G way back in the day. Now it's 5G. For the 5G cell phone network, frequency equals 39 gigahertz, so we'll do it for the same frequency that we did in the previous video. What is the energy of this electromagnetic radiation? We have our equation for energy. We have Planck's constant. And we have 39 gigahertz, which we saw a gigahertz was 1 times 10 to the 9 hertz, and which hertz was 1 over second, or a second to the minus 1. So this 39 gigahertz became 3.9 times 10 to the 10 hertz, or 3.9 times 10 to the 10 seconds to the minus 1. We can see that our seconds will cancel out, leaving us with joules as a unit. And we get 2.58 times 10 to the minus 23rd joules, an extremely small amount of energy, but you get enough of these photons together, or you get enough of these together, you will have, when you get moles of them, you will have enough to create some nice energies. Let's talk for a minute about units here. So the equation gives you units of joules. We can also, since this calculation is done for a single photon, add units of photons, or per photon in this case, because this is the energy of a single photon. It is the joules per photon. Now, we've talked about photons, and we want to emphasize the quantum or quantized nature of photons. So light is quantized. They're only available in discrete whole numbers of photons. And for example, you can have one photon. You can have 2 photons. And as we will see, you can have 6.022 times 10 to the 23rd photons. Which of course would be 1 mole of photons, as we'll see. So 1 photon, 2 photons, a mole of photons are all possible. But a half a photon is not possible. And so quantized basically means you can count them. You can quantify them using whole numbers. Now, things that are quantized in our regular life, or we can think of as being quantized, the typical example is stairs. And the stairs can be thought of, you can have 1 stair or 2 stairs, or 1 step or 2 steps. But what is a half a step when you're going up a set of stairs anyway? So other things that are quantized, you might think that letters are quantized because if you drew half a letter, it would not have any meaning. So atoms are quantized. You can't have half an atom. It becomes something different. So lots of things are actually quantized. And light, even though each photon is very small, as we're about to see in the next calculation, you can only have a discrete or quantized or whole number of them. And as we'll see in this calculation for B, for a 100-watt light bulb, that we have a lot of them even in light bulbs. So the question says, or the example says, a 100-watt light bulb radiates 100 joules per second if we assume that the wavelength of the light bulb is 525 nanometers only. And this is an approximation because light bulbs tend to give off all of the colors of the visible spectrum, well, depending upon what type of light bulb it is. But for the calculations point, we'll just do 1 wavelength. Then the question will then be how many photons are emitted each second? And this is a bread and butter or typical calculation that we will do, or 2 calculations. So we've already talked about how if you have a specific wavelength, you can find energy. So E equals H times frequency. And once you have that, and we have that C equals wavelength times frequency. Now, since we have wavelength, we're going to now solve this equation for wavelength, solve it for frequency, and then plug in to the energy equation. So rearranging this equation, we have frequency equals c, the speed of light, over wavelength, and then plugging that into the energy equation, energy equals h, Planck's constant, times c over wavelength. So here's the equation we're going to use to relate the wavelength that we've been given to energy, and that will be for a single photon. And then we'll talk about this 100 joules per second. So let me come all the way back over here and use up all my space on this. So hc over wavelength, h is Planck's constant, 6.626, times 10 to the minus 34th joule seconds. C is the speed of light in a vacuum, or the speed of electromagnetic radiation. That's 3.00 times 10 to the 8th meters per second. Divided by my wavelength. My wavelength is in nanometers. And in this time, just to do something a little differently, I'm going to put in my 525 right into my equation. And then instead of writing nanometers, since 1 nanometer equals 1 times 10 to the minus 9th meters, I will just write times 10 to the minus 9th meters there. And so that's a shortcut method of doing my unit conversion. When I do this, I get that, so 6.626 times 10 to the negative 34th times 3.00 times 10 to the 8th divided by 525 exponent 9 minus, I get 3.79 times 10 to the minus 19 as the number. And we see that our meters cancel out and our seconds cancel out. So our units here are joules, or as we've already discussed, joules per photon. And now this joules per photon, what we'd like to do is we'd like to use it as a unit conversion factor. Let me show you how that works. I have 100 joules, and I know that there are 3.79 times 10 to the minus 19 joules per photon. So if I put my joules with the number on the bottom, 3.79 times 10 to the minus 19 joules per 1 photon, I can calculate how many photons there are to deliver or in each 100 joules. The only part we need is the 100 joules for this part, because it says how many photons are emitted each second. So we'll start just with our 100 joules. 100 divided by 3.79 times 10 to the minus 19. And I get that there are 2.64 times 10 to the 20th photons. And that is the number of photons that are emitted each second, a very large number of photons. However, remember, photons come in quantized numbers. You can count them, even if you've got to count very high into very large numbers to get to the actual numbers. And I will say that this number will turn out to be on the same general order of magnitude, although it's a little smaller in this example, as moles, so 10 to the 23rd, and we'll talk more about that later. Now, a photon has energy. The energy associated with a photon can move something with mass like an electron, and this is a picture of what's called the photoelectric effect. For the photoelectric effect, when a photon comes into a substance, oftentimes the substance is a metal, because metals tend to have fairly loosely held electrons. When the substance comes in, if it has enough energy, it can eject an electron. So here comes our photon with a specific wavelength. With a specific wavelength, it comes in. If that photon has enough energy, it can eject an electron from the metal. And a couple things about this. So photoelectric effect is this picture here. Next, and we'll call this 1. We'll put it right there. So a photon has no mass. Yet it can push something. And in this case, it can push an electron to leave a metal. This is a photon's wave-like property. As such, the energy associated with a photon can also break a bond. As an example, the energy of an oxygen single bond is 146 kilojoules per mole. The question we're going to ask is, can a photon with a wavelength of 650 nanometers break an oxygen-oxygen bond? This question is similar to at least one that you'll find on the homework, if not more than one, and potentially the exam. Here's how we're going to approach this. We're going to have to find out what's the energy of this photon. We've been given wavelength. So we have wavelength. We need energy. You can do it in 2 steps by taking the wavelength and the speed of light, solving for the frequency, plugging that frequency into the energy equation. Or you can combine these two to get an equation for frequency here, and then plug in for frequency in the energy equation to get a new equation which says energy equals Planck's constant h times the speed of light divided by wavelength, and then plug in. Planck's constant, 6.626 times 10 to the minus 34th joule seconds. Speed of light, 3.00 times 10 to the 8th meters per second. We can see how our seconds will cancel. We can see that we want to end up with joules, and we need meters in the bottom of this. We've been given nanometers. A nanometer is 10 to the minus 9th meters. Whether you put it into the bottom here as 650 times 10 to the minus 9 meters or 6.50 times 10 to the minus 7, those two things are equal to each other. And you can solve for the energy. 6.626 to the negative 34th times speed of light divided by, I get 3.06 times 10 to the 19 times 10 to the minus 19. That's joules. That's the only set of units we get from this calculation, but as we mentioned just prior, that is the energy of 1 photon, so joules per photon. So that's how much energy is in a photon. We know that it takes 146 kilojoules per mole, and that's per mole of oxygen-oxygen single bonds. What we next need to do is find out how much energy is stored in 1 mole of photons to see if they can break 1 mole of oxygen-oxygen bonds. At least that's the approach we're going to take. We have joules per photon. We know that's per 1 photon. If we're going to get to moles, we need to use Avogadro's number. 6.022 times 10 to the 23rd of anything, but in this particular case, photons, equals a mole of that same thing. And then because we're in kilojoules, we'll convert joules to kilojoules. 1,000 joules equals 1 kilojoule. So start with our joules, multiply it times Avogadro's number, divide it by 1,000, and we get 184 per mole of photons. So yes, because this number is larger than 146 kilojoules per mole, the photons, each of them will break an oxygen-oxygen single bond. Can a photon? Yes, because the energy in a mole of these photons, so 650 nanometer photons, is larger. 1 mole of photons has enough energy to break 1 mole of oxygen-oxygen single bonds.